we are discussing about relations, right? Fine. So, okay, so we were talking about relations and we discussed three types of relations, right?
Sir, can you speak loudly?
Okay, am I audible?
Yes, sir.
Yes, sir.
Oh, so we were discussing about relations and we discussed three types of relations. So, so recall what we did so far, a reflexive relation. This we discussed. In symmetric relation, we discuss symmetric relation. We discuss transitive relation. Fine. So basically, what is a relation? Relation among two sets is we define some rule by which we want to relate, right? So a relation is a rule by which we define two elements of a set or elements among two sets, right? So it depends on what are your sets. That is a rule, just rule. Rule can be anything, right? So, and relation is a reflexive means every element is of a relation on some set. Now we are defining relation on set. If every element is related to itself, then it is a reflexive relation. Symmetric means if some element is related to another element, if element X is related to Y, then Y is also related to X. So I will write down the definition. So A is a non-empty set, right? A is non-empty set. R is relation on set A. Then A is reflexive if for every element in A, X is related to X. Every element is related to itself, right? Symmetric means if if X is related to Y, then Y is related to X. You understand the notation, right? Transitive means if X is related to Y and Y is related to Z, then X must be related to Z, right? So these are the simple way to say that when relation is reflexive, symmetric, transitive. So, and notation also I told last time. What notation? Ki pair xy is in relation is equivalent to saying that X is related to Y, right? So this is the same thing. It is equivalent to that X is related to Y with respect to relation R, right? So those who join newly, so they may not understand this, but they should go back and see what is the relation. All these definitions are available here. They should learn what we discussed in the previous lectures so that they can understand. So this is a notation. X pair xy is in R means X is in relation with Y with respect to this relation, right? Or X is related to Y with respect to relation R. So this is the meaning of xy belongs to R is same as X related to Y is same as X is related to Y. So this notation, if you understand clearly, then you can understand further part, right? For example, those who are newly joined, I will discuss one more example. Suppose X is equal to set of family members, right? Suppose in family there are mother and father, two members, right? Two members, mother and father, and they have uh, children. So for example, uh, John, Richa. So I will denote John by J, right? Richa by R. Uh, Sam, I will denote Sam by S. And therefore one more child is there. Suppose uh, Geeta. So I will denote it by this. So mother, father, John, Richa, Sam, Geeta. So what is my set X now? Set X has how many elements? Mother, father, John, Richa, Sam, Geeta. So these are my family members. Right? Now define relation R on set X as for xy belongs to X. So I choose any two family member. Whenever I say xy means I am choosing two family members arbitrarily, and they are related. X is related to y, or X is related to y. Right. So when I say x r y means X is related to y if and only if X is brother of y. Right. So what is my relation when two elements are related? So if X is brother of y, then only there is a relation, otherwise no relation at all. Okay. So now I want to write down my R as a set. What are the pairs? For example, is M related with F? Is M related with F?
No.
No, because M is not brother of, right? So M is not related to F, so this pair is not there. Correct? Now is M related with J? Is M related with R? Is M related with S? Is M related with G? No. So
No.
these pairs are not there. Okay. Now is F related with J? No. If F related with R? No. No. Right. F related with S? No. Right. So fine. Is J related with R?
Yes.
See, John is a brother of Richa, so J is related with R. So certainly this pair is there. But is pair RJ there?
No, sir. No, sir.
Yeah, RJ is not there because Richa is not brother of John. Right? John is a boy, Sam is a boy, Richa is a girl, Geeta is a girl. Right? Therefore, this pair is not there. JR is there, but RJ is not there because with respect to this relation, R is not related with J. Right? Is JS there? JS there?
Yes.
This yes, this pair is there. John is brother of Sam, and Sam is also brother of John, right? Right, because Sam is brother of John. Both are boys, so so this pair is there in this case. Fine. Is JG there? Pair JG.
Yes.
Yes, sir. Yes.
JG is there because John is brother of Geeta. Fine. But pair GJ is not there because Geeta is a girl. So, right? Fine. Now check for RS. Is pair RS there?
No, sir.
No. But SR is there.
Yes, sir is there.
Right. Now is RG there? RG?
No, sir.
No, because Richa is not brother of Geeta. Geeta is not brother of Richa. So RG, GR not there. RG, GR. So these two pairs are there. Right. Next are the SG. SG is there, but GS is not there. Right. So how many pairs are there in this relation? 1, 2, 3, 4, 5, 6. 6 pairs are there. Right. And therefore you can understand ki if some XY is there, not necessarily YX is there. Now is this relation reflexive?
Sir, will JJ will be included?
Yeah, You can say in this case. Very good. JJ and SS.
SS.
Right? JJ and SS. Because you can say that John is a brother of himself. That you can understand, right? Right. Because John is a boy. So is this
It is
relation
not reflexive.
not reflexive? Because
Not reflexive.
RR is not there. GG is not there.
GG is not.
Okay, MM. Can I include MM?
No.
FF.
Yes, FF.
FF can be included.
Yes.
F is a father. So
Yes,
father
sir.
is a brother of himself. Right. Very good. So MM is not there. RR is not there. GG is not there. So it is not reflexive, because for reflexivity, every element related to itself. Right. So for example, Richa is not a brother of Richa. So that is not there. It is not reflexive. Is it
Sir,
symmetric? Yes.
No, sir. It is not symmetric.
sir, I
Not.
have a doubt.
Yes.
The relation we should define should be X is brother of Y. So we can understand JJ and SS, but FF will be father of himself if we assume like that. And X should be brother of Y, no? Then how we can take FF?
Father is a male.
Yes.
So you can say that, like John is a brother of himself. So father, you can say that he is a brother of himself.
Okay.
Don't worry about who is a father of father or mother of father. So grandparents are, doesn't matter in this case,
Okay, sir.
right?
Thank you.
Well, so is it symmetric?
Yes, sir.
JR is there, but RJ is not there, so it is not symmetric, right?
No.
Whenever JR is there, RJ should be there for symmetry, but this is not symmetry. Symmetry means what? Symmetry. Symmetry means XY, YX. Symmetric, right? Fine. Is it transitive? Is it transitive?
Yes, sir.
X is
Yes.
brother of X is brother of Y and Y is brother of Z. Then certainly it is
Yes.
right. So you check that it is transitive, right? So this is not reflexive, not symmetric, and transit. So you check this. Okay, so you change your relation. You can define relation. Ki suppose among same family members, you can define another relation. Ki two members, please keep your mic off. Somebody have kept mic on. So if you can define the on same family members, you can define another relation. So X is related to Y. If X and Y, X X is sister of Y, like that, right? X is a sister of Y. So in that way you can define. Or X is related to Y if they like same kind of sweet, or X is related to Y if X and Y are they like same movie, whatever you define. But there are many relations you can define. That is what I want to tell you, because we are dealing with such kind of mathematical concepts in our day-to-day life without realizing it. That is what I want to tell you, right? And therefore mathematics is very essential in our life, because it is about philosophy. If you understand mathematics, you can understand philosophy of life. What is after all mathematics? Mathematics is a philosophy, right? So how things behave, and that is happening in our mind. We are thinking, imagining what is happening, what logically happening, right? So, and it is happening around every day, at every instant, right? So for example, you are sitting in a hall and there is a mathematics, lots of mathematics in this room, particular room. For example, air particles are moving here and there, then every particle has a velocity and then there is a velocity vector, right? So you look at the room, then this your room is a three-dimensional, and then you can fix origin and there are axes and all these things, right? So the many things are happening around us, and everything can be described using mathematics. Right. So that should be the approach while learning mathematics as a BSc students.
सर
Right. Yes.
सर बट ते जे जे स्वतःचा स्वतः कसा भाऊ असेल म्हणजे
See, you boy is a brother of himself. Yeah, that you can that you can say, right? Because what is a brother? Brother is a male, right? Brother means male,
यस
right?
बट
Suppose,
द ब्रदर दुसऱ्यासोबत रिलेशन असतं स्वतःसोबतच कसं असेल
see, this is you can think over it. की त्याच्यावर तुला विचार करायला पाहिजे की एखादा एखादा मुलगा स्वतःचा भाऊ असतो का? की सपोज फ्रेंडशिप, एक्स इज फ्रेंड ऑफ वाय, एक्स इज रिलेटेड टू वाय, इफ एक्स इज फ्रेंड ऑफ वाय, तर एखादा माणूस स्वतःचा फ्रेंड असतो की नाही?
हो
मग तुम्हाला फ्रेंड असायला दुसराच माणूस पाहिजे का? आपण स्वतःची काळजी घेतो म्हणजे आपण आपल्याला स्वतःला फ्रेंड मानतो की नाही?
यस यस सर
राईट. सो सेम थिंग.
ओके
ब्रदर असण्यासाठी काय पाहिजे की ते एका एका फॅमिलीचे पाहिजे, त्यांचे पेरेंट्स सेम पाहिजे. राईट. एक्स अँड वाय एकमेकाचे ब्रदर आहेत, त्यांचे पेरेंट्स सेम पाहिजे आणि मेल
हो
पाहिजे. आता जे आणि जे सेम माणूस आहे, त्यांचे पेरेंट्स सेम आहेत.
यस
Right, so you can say that ki J is a brother of J. So see, that's why I'm saying ki it is a philosophy. Right, so how
ओके
do you look at the things? How do you look at the things? Okay, well, so I think there is no doubt in the definitions of relations, ki what is a reflexive, what is symmetric, and what is transit. And then why I want to go to the next thing. See, what to do with these relations? So what to do with this relation? So the equivalence relation. So let A be a non-empty set. A relation R defined on A, a minute, a relation okay, so relation R are defined on set A is said to be an equivalence relation if it is if it satisfies all these three properties: reflexive, symmetric, and transitive. So, if relation satisfies all the above properties, reflexive, symmetric, transitive, then such relation is called as equivalence relation. Right. So, for example, so yesterday we discussed many relations, right? And let us start with simplest. Suppose A is equal to A, B, C, three element set. I define a relation. For example, empty relation. Is it a equivalence relation?
No.
No, sir.
No, sir.
No,
नो
So
सर
sir.
इट
it is
No.
not
No,
equivalent.
sir. Empty relation is not reflexive.
So not
Because
equivalent.
it is not reflexive.
Right. So it is not reflexive. So not equivalence relation. Fine. So if I define another relation A, B, B, C, C. So is it equivalence relation?
Yes, sir.
Right. So it is equivalence relation because it is reflexive, no doubt, because every element, there are three elements in set A, and A is related to A, B is related to B, C is related to C. Every element is related to itself. So clearly it is reflexive. It is symmetric because there is no pair like AB, so we do not worry about BA. Right. So there is no evidence there is AB and not BA. There is no evidence that there is X related to Y, but Y is not related to X. Right. So our transitivity is clear by saying we cannot produce an evidence. Right. So A, B, B, C, C, A,
Sir,
C.
I
Yes.
have a question.
Yes.
How is R2 transitive?
What is a transitive? When relation is not transitive? When relation is not transitive? Just recall what we discussed yesterday.
Okay.
Right. What is a when relation is not transitive?
When X is related to Y and uh, the next relation is not starting from Y. Okay. Huh.
Right. So if you can produce an evidence, so when you say that R is not transitive, when you say that the R is not transitive, if we can produce evidence, A is related to B and B is related to C, but A is not related to. If you can produce such evidence, then you
Okay.
can. One evidence is sufficient, right?
Thank
Right.
you, sir.
So for not transitive, we need to produce an evidence such that X is related to Y and Y is related to Z, but X is not related to Z, such evidence. But here we cannot produce any evidence at all. Right. So in R2, there is no such evidence at all. So you have to accept that it is transitive. Right.
Okay, sir.
Okay. So R3 is related to A, B related to B, C related to A related to C. So is it reflexive?
Yes, sir.
So reflexive.
Yes, sir. Yes.
Reflexive. Is it symmetric?
No, sir. No, sir.
No,
Not
sir.
No,
because A is
no,
related
sir.
B is related to C, but C is not related to A. Is it transitive?
No, sir. No, sir. Yes, sir.
A is
Yes,
related,
sir. Yes,
huh,
it is transitive. It is
uh,
transitive.
right. So A is related to C and C is related to C. So A related to C. So you check all the pairs. A related to C is there. Now C related to C there. So what we expect that A related to C should be there, which is there. A related to C. Right. You can check for another pair. So what are possibilities? A related to A, A related to A and A related to C. So we expect that A related to C, which is there. Fine. So there is no evidence, right? So it is transitive. You check this. If I am missing something, then you clear it. Fine. I R4 A B B C C. For reflexivity, the all these pairs must be there. Otherwise, if you are missing one pair, then it is not reflexive. So A C B A. Right. So is it equivalence relation?
Yes, sir.
Yes,
Yes, sir.
it is.
Reflexive?
Yes, sir.
Yes,
It is
sir.
a
Symmetric? Yes. Transitive?
Transitive also.
Right. So this is equivalence relation. Equivalence relation. Fine. Now you understood the definition of equivalence relation. If it is satisfying all the three properties, then it is equivalence relation. So for example, let us see the X is equal to set of all lines in the plane. Right. So I define relation. What is my relation? Line L1 is related to L2 if L1 is parallel to L2. Right. So is R equivalence relation?
Yes, sir.
Yes, sir.
Right. So is it reflexive? You check this.
Yes, it is.
Yes, reflex.
Every line is parallel to itself.
Reflexive, symmetric, and transitive.
So if two lines are parallel, then if x is parallel to y, then y is parallel to x, so it is symmetric. If x is parallel to y and y is parallel to z, then x is parallel to z, so that is also true. So all these three properties are. So you check this. Check this. Right. Later on you can check this. So if I define relation R1, L1 is related to L2 if L1 is perpendicular to L2. So is this relation equivalence relation?
No, sir.
No,
No, sir.
No,
it is
sir.
not.
It is not
Because
reflexive.
it's not symmetric.
It is not
Right. First
It
of all,
is not reflexive. It is
reflexive.
it is not reflexive and not transitive. It is not reflexive and not transitive because
Transitive.
line x is perpendicular to line y, and see, this is my line x and this is my line y. X is perpendicular to y and y is perpendicular to z. Then x is not perpendicular to z, x is parallel to z. Right, x is perpendicular to y is perpendicular to z, then x is not perpendicular to z, so it is not reflexive. It is symmetric but not transitive.
Transitive.
Excuse me, sir.
Yes.
Sir, if we take this line in 3D system, then we say that x is perpendicular to z in
No,
3D
here
system.
what is my set? All lines in plane.
Okay.
Right, so my set is very clearly defined. It is lines are in plane only. They are not in three-dimensional space. Right. Okay, so that you can think about three-dimensional space. That is a different thing. If you want, you can work out that example. Fine. Okay, so let me tell you one more. Okay, let us not go to the example. Now, I want to explore more things about relations. So let A is non-empty set, R is relation on set A. So R is a relation on, so R is a relation on set A. So what is use of these relations and equivalence relation? Right, that is what I want to understand. So fine. So A is a non-empty set and R is a relation on set A. So see, you have to be, you should be confident about whatever I am writing. I am writing and you are confident what I am saying. A is a non-empty set and R is a relation. So now you have clear picture about the relation. What kind of thing is relation? So suppose okay, what I want here, I want to define equivalence class. What I assume is, I should assume that relation is suppose R is an equivalence relation. Suppose R is an equivalence relation. Suppose R is an equivalence relation. Right. So let I choose any element x belongs to A. Right. So do you understand what I am doing? What I am writing? So you do, are you following me? Right.
Yes, sir.
So A is a non-empty set, R is a relation on set A, and suppose R is equivalence relation. Now I am choosing arbitrary element from A. Equivalence class of X with respect to relation R is the set of all elements in A which are related to X with respect to relation R. So definition is clear.
Yes, sir.
So what is the equivalence class? Equivalence class of element X is all those elements from set A which are related to X with respect to this relation. We'll see example, then it will be very clear. So equivalence class of X is denoted by this notation, bracket, square bracket X or X bar. These are the notations anyone you can use. So equivalence class of X is denoted by this notation. So thus, what is X equivalence class of X or X bar is a set. And what type of element this set contains? So this contains those elements from set A which are related with X, right? Or what is this set? Those elements from set A for which xy is in R. And I am assuming my relation is equivalence relation. I am assuming my relation is equivalence relation. Therefore, it is reflexive symmetric transitive. So please keep your mic off. So I am assuming relation is equivalence. So it is symmetric, and therefore doesn't matter I write xy or yx. Only thing is ki those elements which are related with x, right? So just choose any x, and what are the elements related with that element. So such things we can put in this, right? So the example, if we see this, we'll start with simple example and then we'll try to understand this. Right, and I define a relation is A because I basically want equivalence relation whenever I talk about equivalence class. So I need equivalence relation. So AC CA. So is this relation equivalence relation? Is this relation equivalence relation?
Yes.
Yes,
Very
sir.
So should
Yes,
A
sir.
should be A, comma B,
Yes,
comma
what?
A comma become a C.
Set A.
The example A,
Oh
set
oh
A.
A B C, three element set. Fine. Now now R is an equivalence relation. Right, so that you should explain why. Right, so second point, what is now I want to write get the equivalence classes of each element. So what is equivalent class of A or A bar? Right, so what are the elements which are related with A? What are the elements which are related with A with respect to this relation? So is A related with A?
Yes,
Yes.
sir.
Yes, sir.
A is in its class, right? Is A related with B?
No.
No, sir.
No, so B is not
No.
equal.
No, sir.
Is A related with C?
Yes.
Yes.
Yes,
Yes,
sir.
sir.
So C is
A
in its
related.
class, and therefore what is equivalence class? So A and C, because A is related to C, C is related to A is related to A, C is related to C. So C is in this class, right? Fine. Now I want to write down class of B. Now is B related to B?
Yes,
Yes.
sir. It is
Yes.
related.
Yes,
Right.
sir.
I have to identify elements from set A, those are related with B. So that is my job. So B is related to B, so I will put B in this class. Is B related to C? B related to C?
No,
No, sir.
No,
no,
sir.
sir.
It is only element.
No, sir.
Yeah, exactly. It has only one because B is not related to A also. Fine. Now, what is the class of C? Is C related to C first of all? Yes.
Yes.
Yes,
Yes.
it is
Yes.
related.
Is C related to
A
A?
is also.
Is
Yes.
C
Sir.
A.
A? Is
A.
C related to B?
No.
No.
No. And observe that these two sets are equal. This is a simple observation. All right. So, what are the observations? What are the observations from this? First observation is class of A is equal to class of C as a set, right? Because this set has two elements A and C. This set has two elements A and C, right? As a set, they are same. Doesn't matter which element is first and which element,
So
right?
there is no effect of order.
Set. Suppose it is a set of, if you have a set of 10 students, 10 students, student 1, student 2, student 3. Doesn't matter ki which element I put at first position. As a set doesn't matter, right? Suppose you have,
Yes.
so if you have a bag containing fruits, and first fruit is a banana, second fruit is a apple, third fruit is a orange, and so on. Suppose you vacate this bag and you took out all the fruits, and again you put in the bag. Is the set is the same set,
Yes, sir. No.
Yes,
right?
sir.
It is same because
Yes, sir.
Yes.
you just took out the fruits and again put in the bag. So same set, same fruits. Only thing is the banana was initially banana was
Order is different.
so banana was here, apple was here, then orange was here. Again, if you took these fruits out and again fill in the bag, now banana is here, then apple is, and so on. But the as a set is the same. Doesn't matter where you put the elements in the set, right? So that you need to understand. When we say set, it doesn't matter which element is where. Correct? Fine.
Yes, sir.
Therefore, so these two sets are equal, right? So therefore, equivalence classes of A and C are same. This is the first observation. What is the second observation? What is the second observation? Equivalence class of A and intersection with equivalence class of B. What is the intersection of equivalence classes of empty,
None.
right?
City.
Empty.
And equivalence class of A is
Empty.
same as equivalence class of
Empty.
C. Again,
Five.
this is also empty. Equivalence class of C and equivalence class of B. Because equivalence
B.
class of A is same as equivalence class of C, right? So that is same thing. What is third observation? Third observation. Third observation, equivalence class of A and equivalence class of C is same. So union with equivalence class of B, I will get entire state A. Am I right?
Yes.
Yes.
Okay, so these observations are very essential, and we are going to prove this we want to generalize these observations for general set and general equivalence relations, right? So these are the observations for this particular case. Now, why equivalence class of A is same as equivalence class of C? Because C is a member of equivalence class of A, and therefore how their class can be different? Right. So what is A? A is a representative. You can choose any member as a representative. Right. So note this. If X is an equivalence class of X, then X is called as a representative of its class. Right. So it is a representative. Now, if you are in the class, right? In this particular situation, you can choose anyone as a representative, no matter which. Here I am saying A is a representative of this class. Can I say that C is a representative? Do you understand?
Yes,
Yes.
sir.
Yes, I can select C as a representative, and therefore class is not going to change. Whoever representative from the class you are selecting, class is not going to change, right? Therefore, either you select A or C as a representative, their class must be same, right? That is what the fact we want to observe, right? Okay, let me give you one more example which is very relevant at this situation. X is equal to set of all the students in college. Right? So in Ferguson College, there are many students, many things. So X is a set of all students. Now you understand what is the meaning of all. FYBSc students, all divisions. SYBSc students, all divisions. CYBSc students, all division. Arts students, BA students, FYBA students, SYBA students, MSc students, MTech students, right? So computer science students, animation students, all whatever students are in the college. Uh, I have this is a ground, playground, and all students are gathered here on this ground, right? All the students of the college. Now I am going to define a relation now. To define relation R on set X as for two students in X, this student X is related to Y, X and Y are from same class. Do you understand what is the meaning of same class? Forget about equivalence class right now. We have all the students in the college. We have all the students in the college, and all students are gathered here, right? And now I am defining relation on this set. If two students are related, this student and this student are related if they belongs to same class. They are uh, suppose I take X is equal to some student from FYBSc A division, right? Suppose I as a to be very specific, I will select name of some student Adarsh, which is in A division, for example, right? So X is Adarsh, right? She is from FY A division. Now, first of all, I would like to ask the question: is R equivalence relation?
Yes, sir, it is.
Right? So is it equivalence relation? So if you choose any student from your class or in the college, suppose I select arbitrary student from this card. Is he member of his class? Suppose I select a student. Is student X is a member of is X and X from same class,
Yes.
Yes,
Yes.
sir.
right?
Yes.
And X and X are from same class because whatever its class, he's from animation, FY animation or bioinformatics, biotechnology class, or he's from FYBA class. But X is suppose from FYB and same X I am saying they are from same class, right? So the every student satisfy this condition. So it is a reflexive relation clearly, right? Is it symmetric? If
Yes.
X and Y are from same class, then Y and X are from same class, right?
Yes.
Yes.
So
Yes, sir.
check this.
Yes.
So you write down the proof. It is equivalence relation. Fine. Second, what are the equivalence classes? What are the equivalence classes? So suppose I will just select one student from this group of students, which are those all students are gathered on a playground, and I will choose one student. Suppose he is from FYBSA division Adarsh. Now suppose I pick Adarsh, as a representative. I will choose Adarsh as a representative, and I am going to construct his class. So how I am going to construct his class? Right? I will choose all the students from this. I will look at all the students. Those are related with Adarsh. So how they are related with Adarsh? What is my relation? The class, right?
Same class.
Same
They
class.
belongs to same class.
So I will choose identify students. Those are who are from Adarsh class, from class of A, right? And in this way, what I will get now? What I will do now? Okay, let me draw the
The whole
picture.
class.
Set
Right.
A,
Suppose
set X, I mean.
Adarsh is standing here, and from this gathering, I will take away all the students from his class. Right. So I have separated out all the students who are from FY BSc A division. Am I right? And Adarsh is representative of its class, for example. Right. Now from the remaining student, is there any student from A division? Right.
No.
I have
No.
already, I have already separated out all
No.
the students who are related with others. So no student is remaining. So therefore, what is the in remaining gathering? No students from A division. That's it. Now, now this class is constructed. Now, what is my next job? I will choose arbitrary students. So suppose that student is from B division. Right. So that student is from B division. Now what I will do, I will separate out all the students who are those are from FY BSc B division. Right. I will put them in this class. Right. I will put them in this class. Okay. Now this is a now remaining gathering. There is no student from A division. There is no student from B division in the remaining students. What I will do next time, I will choose any one student. Suppose he is from FYBA, FYBA A division, for example, Arts A division. I will choose one student. What is his name? Suppose Sam. Right. I will select Sam and I will collect all those. And suppose Sam is from FYBA A division. Then I will separate out all the students from FYBA A division. So its class is constructed and Sam is a representative. Here Adarsh is a representative. But suppose I would have selected somebody else, not Adarsh, right? So you can understand there are many students available. Suppose I have selected Aditi Nimbar. So if I select Aditi, for example, yeah, would I get the same class?
Yes.
Yes.
Yes, sir.
And therefore, so doesn't matter which representative I select, I will get same class. If that's the new representative is from A division and I collect all the students which are related with Aditi, then I will get same class because others will automatically will come in that class.
Yes, sir.
Right. So therefore
Yes, sir.
doesn't matter what representative you choose. And therefore that is what exactly the observation we made in the previous case. It doesn't matter what is your representative, C or A. If they belongs to same class, their class is exactly the same seat. Right. In this way, what I will do, I will in this way I will just construct all the classes. Right. Right. So what is this collection of classes? Right. What is the collection of classes? So okay, so I will call this as class 1. I will class 2, class 3, class 4, class 5, and class 6. So I get the set of classes. Right. Fine. So what are equivalence classes? Yeah, do you understand what are the equivalence classes now? So R is the equivalence relation. What are the equivalence classes? Each class is a particular class in the college, right? What are the equivalence classes? Okay, suppose in the college there are 6 classes, for example, 6 classes C1, C2, C3. Then what is the set of all equivalence classes. Set of all equivalence classes. What is the set of equivalence classes? C1, C2, C3, C4, C5, C6. There are suppose 6 classes. Then this is a set of sets, set of classes, right? This is a set of sets, that means set of classes, right? And now what are the objects in this set? Suppose I want to choose an object, so I will select C1 as an object, but C1 itself is a class, right? I will select C4 as an object, so C4 itself is a class, right? Do you understand? Now set of sets, so set of sets are set of classes. So now do you understand what are the classes now? The idea about classes is clear, equivalence classes is clear now.
Yes, sir.
Yes, sir.
In this particular
Yes.
example, the equivalence classes are the exactly classes in the college. Right? Equivalence classes are exactly the classes in the college. And observe that two classes are disjoint. FY-BSc A division and FY-BSc B division. They are disjoint. There is no common student. Does there exist a student who is from FY-BSc A division as well as B division? Such situation
No,
does
sir.
not arise, right?
Yes, sir.
This is what the observation we made here. Any two classes are disjoint. Any two classes are disjoint. And you choose any representative, their class is same, doesn't matter which representative you select. And if you combine all these classes, if you take union of all these classes, what will get?
Set
The
of all
complete
students
set.
in
Students of
college.
all college.
Yes,
Students in
Students
college.
in college.
very good. Suppose I built a walls around this and I constructed classes, and next time I will remove these walls, then I will get again the set of all the students. So therefore union of all the classes is entire set, right? Union of all the classes is entire set. That is what the important thing about these classes. Fine. So suppose let me make a note. Suppose R is an equivalence or let me write down it differently. Equivalence relation is generally denoted by a symbol. This special symbol, right? So this is a special symbol for equivalence relation. So this is read as tilde, or tilde, whatever. So it is read as a tilde, or you can say equivalence relation, the symbol for equivalence relation. So this is a special symbol for equivalence relation. And many times at the different occasions you write down key 1.999 is similar to, right? So similar or exactly similar, or 1.00001 is similar to 1, right? Not exactly same, so it is similar but not so. But anyway, we are talking about equivalence relation, and general equivalence relation is denoted by this symbol, special symbol tilde. Fine. So if uh, is okay, let me not say this immediately. So if R is equivalence relation on A, then the set of all classes of A with respect to relation R is, if R is a equivalence relation, so equivalence relation, I am assuming equivalence relation, not just relation. So then the set of all equivalence classes, right? So a set of all equivalence classes with respect to relation R is denoted by the symbol A modulo R. How it read as A modulo relation R, A modulo relation R. Right. So, and what is this set of equivalence classes? This is a set actually. So, X bar such that X bar such that X is in. So, what is the X modulo R? Right. Let me make it more precise. So, this is a collection of elements in A, and X bar is equivalence class of
R.
X. Equivalence class of X with respect, right? If you change the relation, your classes will be changed, right? If you change the relation, classes will be going to change. Suppose if I make a relation, the same set of all students in the college, and I make a relation, I will define a relation. Two students are related if they like the same sport, right? Suppose two students like football, then they are in same class. But one student like kabaddi and like they same class. Am I right? Am I right?
Yes, sir.
Say that one student X is, and that assumption you can make every student like exactly one game. That assumption you can put there, and therefore no students is in two different classes. So make assumption that every student like exactly one game first of all, and then two students are related if they like same sport, same game, same sport. They are interested in same sport. So if X and Y are interested in cricket, then they belong to same class, and therefore how will be the classes? Right. So if I change the relation, here my relation was they belong to same class. But if I make relation ki they like same sport, then my classes are now different. The set of students is same, because classes will be different. It may happen that ki, with respect to our original FYBSc A division, two students from A division may not be belongs to now same class with respect to new relation, same sport, right? Do you understand the example?
Yes, sir.
Right, and therefore if you change the relation, your classes are changed. So therefore, what is the collection of what is A modulo R or A by R is the collection of all the classes, equivalence classes of members of A, and what is X bar? X bar is an equivalence class of X with respect to relation R. Right. So these are the classes, and whatever if I choose another relation here in case of set ABC, then you can have different classes. So this is what uh, meaning of equivalence relation and equivalence class. So okay, next time we'll see more about equivalence classes and more examples. Right. So any doubt?